We have the code for the puzzle solver's breadth first search. We have the variables and list up here. The user inputs the level of difficulty 1, 2, or 3, and we choose the puzzle based on that for the start puzzle. We start with a root state based on the user's choice and add in a root node to the queue, and we add that root state to the number of check states, or sorry, the list of check states. After we do that, we're going to go to a while loop and we're going to make sure that the queue is not empty or the solution hasn't been found. And as long as those conditions haven't been met, then we're going to keep trying to solve for the solution. So now if we go down to the solve function, we'll see that we take the first node from the queue, pop it off, and remove it. We go ahead and check to see if that particular node matches the goal state. If the state of that node matches the goal state, then we're going to go ahead and try to trace the path back all the way up until the root. And then it'll print it out. If we don't find it though, then we're going to go to our successor function of the active node. The successor function will go ahead and look for where the blank space is, and then after it finds where the blank space is, if it's not on one of the edges, it'll go ahead and move it in that particular direction. So if it's not on the left edge, it'll go ahead and move that blank space left. And when I say move, what it's going to do is it's going to figure out what the cost is of that move, because it'll look at what the tile was to the left, right, up, or down of it, and then it'll input that information into creating a new child node with the direction of the move. That child node is then added to the list of children for the original state that it comes from. After all the children have been gotten, we're going to check to see if that child has already been checked. If that state has already been visited, we don't want to add that child back to the queue. If it hasn't already been checked, we'll go ahead and add it to the queue, and then we'll add it to the check state so we don't visit that state again in the future. We'll go ahead and take a look at the code for the other searches. This one is depth first search. You'll see the only difference here is that we're putting a count and starting at 0, and then we add the nodes to the queue starting at 0. So we're adding the nodes at the beginning instead of the end of the queue. Iterative deepening, same as depth first, except for we have a for loop here, and we clear out the queue and the states that have already been checked. And then we have a depth here in the solve function, so that if the node reaches that depth, then we know to return and start anew once all the nodes have reached that depth, because it'll go all the way until the queue's empty. Uniform cost, it'll be similar, except for we're going to check to make sure that we haven't found the best possible one. So we'll check if the total cost is greater than the best found cost. If it is, then we know we found the best possible one. Otherwise, we'll keep looking. And then the difference here is going to be that we're going to be sorting the queue by the total cost. And so you'll see here there's a sort queue and a comparator that compares the two nodes in the queue. And then what we're going to do is we're going to take a look at best first. It's going to be similar, except for best first is going to have a heuristic of the number of misplaced tiles. So you'll see here there's a function to calculate how many tiles match between the given state and the goal state. And again, you'll have a sort queue, but this time it'll be compared by the misplaced tiles. Puzzle A star 1 will have a similar thing, except for A star 1 will be the number of misplaced tiles plus the total cost. So you'll see the comparator shows misplaced tiles plus total cost here when sorting the queue. For A star 2, we're going to be looking at very similar to A star 1, a heuristic, but instead this time we're using the Manhattan distance. So you're going to see here that we're looking for the distance in the grid, whether it's up, down, left, or right, and then we're going to total that result to find the Manhattan distance. And when we compare, using our comparator, we're going to compare the Manhattan distance plus the total cost. And for A star 3, we're going to look at a heuristic that sums up the misplaced tiles cost. So it'll take a look at 8 plus 7 plus 2 plus 1 and say, okay, the sum of those is 18. So we're going to add the sum of the misplaced tiles, 18, to the total cost. So you'll see down where the comparator is that we're summing the misplaced tiles plus the total cost and comparing that to another node when we're doing our sort of the queue. Here we'll see the run of puzzle solver breadth first search. We'll type in 2 for the medium, and you'll see that each of the steps is represented here. Shows the total cost after each step, and then it shows the total number of nodes popped in the queue max. Best first was one of the few searches for me that worked on the hard level. So if I type in 3, it'll solve it, and I managed to solve it with a total cost of 296. Nodes popped 1800. Here's A star 3 at the medium level. You can see that it shows the steps, and it popped off 18 nodes.